Hey guys, I love all the conversation. It's awesome, for one, but we got to move on to the next talk that Peter's also putting on. But for real, I'm sure Peter and Ed will have plenty of time after this. I actually need to hand this over to my friend who wanted to do the intro for Peter today. Actually, we voluntold him to do the intro to Peter today.
Oh, great.
Oh, John.
I'm also going to need a little help getting my. Does anybody know anything about computers? Oh, hey, there we go. That's cool. So, we can do an intro? Am I waiting? Am I going?
No, I think they said they were going to do an intro.
Okay, so we'll wait.
You got a fun story?
Fun story. I have a physics joke.
Let's do it.
So, Heisenberg's driving down the road. No, let's go with Schrodinger. Schrodinger's driving down the road, gets pulled over by a cop. Cop walks up to him. He says, "You know you were going 55 miles an hour, and it's in a 30-mile-an-hour zone." And Schrodinger looks at him. He says, "Oh, gee, thanks. Now I don't know where I am."
I already set the baseline here.
All right, that sucks.
Joe?
I'm sorry.
It wasn't the worst I've heard from you, Peter. I'd like to introduce the man, the myth, the legend, Peter Bordow. A man who's near and dear to my heart. Truly one of the best men I've ever met. The guy who made the person I am today. He's also...
Don't say that. Oh, shit.
And there's always a but.
I'm not taking credit for that.
But he's also an accomplished guy in his own way. He's a dude who tripped my mind, made me think about things in a more horrifying way. And ideally, he can do the same to all of us here. We can leave with a much heavier heart and much more fear. But it could be an alternative. We will see. Peter, please begin.
Thank you, Joe. Hello, everybody. Thank you for having me here. Second year in a row. I'm surprised I got invited back, which is good. So that's like, here's who I am, right? Okay, so that's my title. And a lot of what I do is I deliver keynotes and I do lectures, and I do them all over the world, and I do them mainly for my employer, right? So Wells Fargo pays for me to do all this stuff, but not today. Today, I get to do whatever the hell I want to do, which is pretty cool. So last year, Sean and Joe and Ed and everybody got me to come out here and do all this, and one of the things they said to me is, don't just do what you do every day for Wells Fargo. Don't come here and just do one of these tech presentations and be dry and, you know, don't make it by rote. So they said, one of the things they said was, bring all of yourself. Now, they know me pretty well, right? And they're unfortunately getting to know me more. So I did. So I'm going to tell you a little bit about me that I almost never share publicly. And then I'm going to tell you, we're going to cover a little bit about the history of where we got, how we got to today in quantum technology. We're going to talk a little bit about quantum physics. You don't need a degree or anything like this. This is meant to really inspire you and get you thinking, but you need to know a little bit about physics to get into the rest of the conversation. And then we're going to talk about quantum technology and all the amazing things that are on the horizon. And then we're going to follow up with, oh my God, the sky is falling and we're all going to die. All right. So, okay. So how did I get here? Well, I was coerced into coming here. No. And I think part of this got answered in the panel. Who was here for the previous session? Raise your hand. Okay, cool. So Ed Vasco and I just did a little fireside chat thingy. So I've known Ed for a very, very long time. And Ed is the head of the Cybersecurity Institute at BSU, and obviously being friends, he made the connection to the festival folks here, and Sean and all the others got me to come out here, and so I'm here because of the friendships and the relationships that I have had and now have, and so that's really important. Oh yeah, so that's Ed. Ed, stand up. Oh yeah, I warned you. You were slide 3. I warned you. That's a great picture, too. That was like 20 years ago. Yeah. Okay. Yeah, right. Okay. All right, so let's get through the next stuff about me. I really hate doing this, but it provides some context. So I'm a bit of a schizophrenic or fractured personality. I am a technology guy. I get paid pretty good to talk about the latest, greatest emerging technologies and hopefully save the world from the quantum menace that's coming. But I'm also a musician. Joe alluded to that. last year I stood up here and I actually played a song, right? I brought my guitar and I did a song and I did a number, and I don't really know how it went because it was like an out-of-body experience because of performance anxiety and all of that stuff. But was it epic? Thank you. So stay tuned, because next year, and here I'm making the declaration, I'm coming back next year with my guitar and hopefully a roadie, and I'm going to do like an opening act, a full set, okay? So, and make sure there's lots of alcohol being served and all that, because the more you drink, the better I'll sound. And I'm also really into martial arts. So I've had a real lot of ups and downs in my life. And wellness was part of that up and down journey. And martial arts is one of the things that saved my life physically and mentally. And that translated into doing these insane obstacle course races. You've heard of like Tough Mudder and Spartan Race and all that stuff. I've done probably 100 of them in the last 10 years. And it's changed my life and really made me the sore and tired person that I am. I'm also an albino. So I have something called ocular albinism. And I don't see very well at all. I have what's called low vision. So everybody looks the same to me. You're all just a bunch of silhouettes and stuff. Yeah, I don't see a lot of detail, and I'm insanely sensitive to light. And I've had that since I was a kid, and I haven't shared that until the last few years really with anybody. I've hidden it my entire life. But it's all part of who I am here. And I'm also a cancer survivor, which really figures in prominently to why I'm standing here today. So I was almost famous. Actually, I was pretty famous. Back in 2000, I had gone pretty good in my electrical engineering career. I was doing okay, but there were some series of events that got me back into music from being a teenager. I'd not played for like 20 years, and so I picked up my guitar and I started playing, and things just snowballed, man. And I mean, you kind of need to know this. I had the #3 song in the world on mp3.com. I had 650,000 downloads. I won awards. I was scheduled to go on a world tour with Taj Mahal and Johnny Winter. I was signed by a record label in the UK called Woof Records. And literally a couple months before the deal was sealed with the record label and the world tour, I was diagnosed with cancer. And yeah, so I had to change my life, every bit of it. So it took me off of that path, and it really made me re-examine where my life was going to go. And so I threw all of myself into technology. And I had been a pretty good engineer, pretty good, for like, I don't know, this back in the 2000s, so like for 15, 18 years. You know, my career was going okay. But having cancer and then having survived cancer gave me a sense of needing to accomplish something significant, right? It wasn't just enough to have fun. I needed to really leave something behind. And so I got really, really serious about my career. And that really facilitated who I am today. I put all my energy into it, and today I am the Distinguished Engineer and Managing Director for Quantum Systems and Emerging Technologies for Wells Fargo. Long title. The longer your title gets, I guess, the older you are. So I'm getting pretty up there. I also chair the post-quantum cryptographic work group in an organization in the financial sector called FSISAC. That's the Financial Services Information Sharing and Analysis Center. So I get to work with literally some of the smartest people in the world in the science and technology fields. I work with peer banks all over the world. I work with government entities. I work with commercial vendors and all of this stuff, all working to help coordinate and save the world from the quantum menace, which is coming. I do a bunch of other stuff. I have a lot of patents. Now we're up to 34 patents as of Monday, actually. And all of these are in the quantum technology field. Now, I'm not a physicist. I am not a mathematician. But I am kind of inspired, and I work with some of the greatest people. My team, I have a physicist, I have a mathematician, I have a cryptographer, and we come up with some pretty crazy stuff. So we do a lot in this space of innovation. I'm also the author of a lot of papers, and I've won a bunch of awards and all that crap. Okay, so let's move along. So let's talk about physics. How do we get to today? So classical physics, several hundred years, we rely on the world as we can observe it and as we can measure it. And this has taken us really, really far. Up until the beginning of the 20th century, we had things figured out pretty good. In fact, some of the fundamentals in classical physics we still use today. Newton's theories still help us calculate orbital trajectories. It helps us calculate orbital paths. It's very helpful in space flight. So we still use a lot of the fundamentals that have stood the test of time. However, early in the 20th century, something really amazing happened. A bunch of scientists, one of them you probably know, Albert Einstein, Niels Bohr, and others I'm sure you have heard of, all of these great minds began to redefine the world. Not just the world, but they began to redefine reality itself, the very essence of what space-time is, the realization of the atomic model, like how particles behave, the nucleus, the electron, the radio waves, the wave-particle duality, all of these things, modern thinking, modern physics, all came out of the work that was done around 1924, 1925. And a lot of it today, everything today really relies on that, right? All of the RF transmissions, satellite, GPS, all of the stuff that we enjoy today, modern electronics, transistors, everything that we enjoy today came out of that 1925 breakthrough. But a bunch of other stuff came out of that. A bunch of really, really weird stuff called quantum mechanics. So quantum mechanics didn't make any sense. It defined a world that we can't experience. Things like uncertainty, things like fuzzy logic, things like, and we're going to talk about some of these elements, they didn't make sense. They were counterintuitive. You really couldn't get your mind around that stuff. But it was proven, right? So they proved it mathematically, and subsequently over the decades, they proved it experimentally. But what can you do with this crazy quantum phenomenon? Well, I would say in the last 10 years, engineering has gotten to the point that now we can really harness a lot of these quantum phenomenon and use them to our advantage. And that's what I call the second great quantum revolution, right? The first one being 1925, and that gave us satellites, it gave us cell phones, gave us the transistor, gave us computers, gave us everything digital that we know about. But all of that other stuff sort of was on the sideline, on the margin, right? But now all that other stuff is becoming mainstream technologically. So it's no longer digital. Now we're moving to a quantum technology world. So what does that mean? What is quantum? So, okay, we're going to talk a little bit about physics. I'm going to skim over the surface. I told you I wasn't a physicist. I know enough to sound pretty good about it. I know a lot about it, but we're not going to get into the real deep stuff here. So I want to talk about 3 principles in quantum mechanics that are key to technology in quantum technology. One of them is entanglement. So we know, we can demonstrate this over and over and over, you can generate 2 particles from a single source, and those 2 particles are correlated or entangled. And whatever you do to one particle, you get a correlated measurement on the other particle. So let's say, for example, you generate 2 particles, 2 entangled particles, you measure one at point A, say its spin, what direction it's spinning. At point B, the other particle will spin in the opposite direction every time, no matter what. Right? And you can do this over and over and over. And the really cool thing is, it doesn't matter how far apart these particles are, that the correlated measurement is instantaneous. So if you take 2 particles and you send one off to Alpha Centauri, and you measure one particle here and you measure the other particle at Alpha Centauri, instantaneously defying the speed of light, you get a correlated action. And we can prove this over and over and over. Pretty cool. So, and as a sideline, I'm going to get into this a little bit. Remember, since everything is connected, everybody knows about the Big Bang, right? The singularity that started the universe altogether. So think for a minute that there's a concept that every particle in the known universe is actually entangled because it all started in the Big Bang, right? We were all generated at that same singularity. But we'll get more into that in a minute. The second concept is called superposition. So this is the world of uncertainty. So here, this is what we thought the atom looked like. We thought it was nice and predictable. You thought there was a little bit of a core with protons and neutrons, and there were these electrons spinning around, and it was predictable, and everybody drew it this way for decades and decades and decades. But that's really not what an atom looks like, okay? And we know this because we can look at atoms. So what an atom looks like is actually on the right, and it's called a cloud of probability. So there really isn't any electron in any position until you measure it. Now think about that for a second. There is no reality of the electron until it's measured. That's got to kind of cook your noodle a little bit. So at the essence of reality, we know for a fact that nothing is certain. Not the position, the velocity, or any attribute of any particle. In fact, we also can demonstrate that there are no particles until they're measured. All right, so we'll get back to that in a minute. Now we're going to talk about tunneling, okay? So this is kind of a cool concept. There's another phenomenon that says if you have a particle and you have a barrier, and that particle is too weak to go through that barrier, quantum mechanics says that one in so many tries, miraculously, that particle is going to get past that barrier, even though there's no way it could. It's going to do it anyway, and that's called tunneling. So it transcends the laws that we know today of modern physics. And so, cute little graphic there. But that concept, the ability of a particle to pass a barrier even without sufficient energy to do so, is actually the basis for most life on the planet. Without that, there wouldn't be us. I'm going to talk about that in a second. All right, so 3 concepts. You got it? Entanglement, superposition, and tunneling. Okay? Now I want to really cook your noodle.
You already haven't done that?
Okay, no. We're in simmer here. So everything is nothing. I love this part. Okay. So the fact is that an atom, that the smallest unit of molecular building blocks that we know about, right? An atom is almost nothing. In fact, an atom is 99.99999% empty space. Now, I use air quotes and I use real quotes on empty because there's no such thing as empty space. But we'll talk about that separately, okay? There's no such thing. But yeah, at the core, at the nucleus of the atom, right, there's this proton and this neutron, and then there's this fuzzy cloud of probability spinning around it, but really there's nothing there, like literally. So, and here's the analogy. Okay, so this blew my mind when I heard this. So the smallest thing that we can measure is called the Planck length. Max Planck came up with the concept of the quanta, this sort of measurable packet of something, right? That's where we get the term quantum. So Max also defined the shortest measurable length in the known reality, and it's called a Planck length. How small is that? It's really, really small. How small is it? Okay, if you took an atom, and we remember the picture of the atom, right? And you blew up that atom to the size of the known universe, okay? Think about that for a second. So all of the known galaxies, everything, right? So billions of light years across. A Planck length would be about the size of an average redwood tree compared to the known universe. That redwood tree compared to the known universe, that is the basis for all reality. That's what we call a string. String theory, everybody's heard of string theory? What is a string? A string is a vibrating filament at the Planck length. That, my friends, is what makes up the entire known universe. Pretty incredible. So really, everything is nothing. It's not even real. These filaments aren't even matter. They're just vibrating frequencies of something at a scale so small it defies the human imagination to really understand how small they are. So when I say everything is nothing, I actually mean it. It really is a miracle that there's anything here in reality. Okay, so we talked a little bit about quantum biology. So in the last 10, especially the last 5 years, there's been a lot of really amazing work done in how quantum processes support some of the fundamental mechanisms that we know all around the world. And so I've got some examples here. So in everything from sensory perception, so your vision is based on quantum processes. Your taste, your smell, and possibly your hearing, right? So this research isn't all complete. Respiration, energy transfer. So, okay, what is energy transfer? Photosynthesis, and I love this example. So photosynthesis is one of those things that if it wasn't there, we wouldn't all be here, right? We can all agree that it's one of the fundamental mechanisms that keeps the planet going. Well, without that tunneling concept and without the ability for atoms to be in multiple places, particles to be in multiple places at the same time, photosynthesis would not work. It relies entirely on quantum processes. We didn't even know that 5 years ago, but now we can actually prove it. So things like nutrition, how you absorb nutrition in your body, how your cells do what they do, all of these things have at their very core quantum mechanical processes. And we also now know that evolution itself is based on quantum processes, right? So DNA mutation happens because of that tunneling phenomenon. And we could go on and on and on, and this is way more than a 5-minute conversation. But what I want you to get is that quantum technology is not just quantum computers, it's not just AI, it's not just some theory that some guy came up with and it doesn't apply to me. If it wasn't for quantum mechanical phenomenon, we wouldn't all be here. The universe would not exist as we know it today. And what's even better is that it really doesn't exist that it exists, right? Okay. Enough of that crap. Oh, yeah, this is where we wanted to go next. Okay. Yeah. Okay. So one of the things that researchers are working feverishly on is explaining what consciousness is. I mean, this research isn't new, okay, but the research in the context of quantum processes and consciousness is fairly new. And so we know, and I don't have time to go into all of the details, but we know for sure, and it's repeatable over and over and over and over, that if you measure a particle, the particle knows that you're going to measure it before you measure it. All right, now, that seems really counterintuitive, but it can be demonstrated in the lab. You can, with using the correlated particles, right, you can have a pair of entangled particles, and you can try and trick the particles to be a certain state even before you measure them. Turns out you can't do that because the particle knows that you're going to measure it before you measure it. So there's a book if this really fascinates you, if this really turns you on, there's a couple books that you need to read. And one of them here is a friend of mine, Dr. Robert Lanza. He invented this term biocentrism. And essentially, without going into a lot of detail, Dr. Lanza asserts that we, as the observer of the universe, are in fact the source of reality itself. And that the universe knows that we were going to observe it before it existed. And that's why it existed, so that we could observe it. Which actually lines up with all of the quantum stuff that we just talked about. It lines up with entanglement, superposition, tunneling. It lines up with all of that stuff. With all of the crazy stuff that we can't explain, why is there no certainty? Why do particles know that we're going to measure them before we measure them? Well, maybe it's because that's how they were made, by measuring them, by observing them. So, read this book. It's called Biocentrism. If this interests you, it will challenge everything you ever thought about the origin of the universe and the origin of consciousness. All right, enough plug for Robert. Now, I'm not getting any money from that, so my PayPal address is at the end of this thing. Okay, let's get back into quantum technology. God, I just chewed up 24 minutes. Okay, so quantum technology is here today. It is already instantiated in things like quantum materials, machine learning. It's doing quantum sensors are a crazy cool field, quantum computing, quantum communications. It's not just quantum computing. Quantum technology is going to pervade everything. All of those weird sort of quantum processes, we're still figuring out how to use them best. The latest stuff is really around biology and molecular design and communications. But what's coming is going to change the world. I mean, you can't even imagine what this is going to do. It's bigger than the transistor. It's bigger than radio waves. But we don't know how big it is because we're not there yet. Okay, quantum computing. We've talked a lot about it. So what is the quantum advantage? Why is it better? How does it work? So we're going to get into a little bit of that. So when we talk about classical computers, we talk about bits. We talk about a bit being a 1 or a 0. And all of digital science is all based on ones and zeros. There's nothing else, right? There's either a 1 or a 0. It's a light switch. But in the quantum world, in quantum computing, you got the ones and zeros potentially, but you have everything in between a 1 and a 0. Go back to uncertainty, right? We don't know what the state of a particle is in until we measure it. Now, how do we use that to our advantage? Well, because the probability of it being positive charge or negative charge or an upspin or a downspin, that possibility is what is the fundamental basis for quantum computing, what we call a probability distribution. So you can measure a particle over and over and over and over and begin to get sort of a bell curve, right? You can begin to sort of a probability distribution, kind of like tossing a coin. And if you use that with some sophisticated algorithms, you begin to build an ability to predict, but predict in a way that classical computers can't. So here's essentially how some of that stuff works. Well, this is sort of the same thing I was just talking about, right? So when you look at the probability percentages, right, you can arrive at an answer. So one of the things that you can do with this is that you can factor really large numbers, and I'll tell you how that works. So on a classical computer, if you want to factor a 500-digit number, how you're going to do that is you're going to guess. You're going to guess many, 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 many times. And in fact, it has been calculated that, say, RSA 2048 with 2048 bits would take a computer somewhere in the order of about 1 trillion years, given current computing capabilities, to be able to guess the right answer. Well, what if you could guess all possible answers at the same time? Ooh, okay. So that's how this works. So in essence, and I'm dumbing this down a lot because we don't have a lot of time and all that, but in essence, I can write an algorithm that allows me to guess all of the possible answers in a very short amount of time, arriving at the most likely choice. Now, it's not deterministic, it's not absolute, but it's a really good shot. And if I can do that in, say, 10 milliseconds, imagine what I can do in, say, 5 seconds, right? So thousands and thousands and thousands of runs, I can get pretty darn certain that I've got the right answer. That's how quantum computing uses its quantum mechanical properties to that advantage. So where does that show up? Well, it shows up in, where are the cool graphics there? We were supposed to have really cool pictures. Anyway, so it shows up in chemical and molecular science, where we can design drugs and we can design molecules based not on guesswork, well, based on super efficient guesswork using quantum computers, right? We can calculate how these complex systems work on a level that we never could do before. So things like geology and meteorology, supply chain and logistics, optimizing routes for shipping and transportation, designing drugs, being able to calculate the impact of any given molecule on the human biology using computers, never having to do trials again. That could be in our future. Quantum sensors that are so precise they can detect nano changes in electromagnetic and gravitational fields. MRI and CAT scan technologies will feel like X-rays are today. That's how advanced imaging is going to be. Things like brain-computer interface, right? So we've done some primitive work and we can scan the brain waves and all of that great stuff, and through clunky, old-fashioned looking stuff. Quantum sensors promise to change all of that. They could provide a fully immersive environment. If you think Google Glass or Oculus is cool today, imagine not even having to wear something on your face. Imagine a direct interface into your conscious processes, right? So, wow, some scary stuff we're going down. But these sorts of things now become possible. Now, I don't know if we should do them, but we certainly will be able to do them. Oh, and here just some more examples of where all of this stuff really may show up. But I want to talk about cybersecurity. Yeah, so everybody was here for the last panel. You figure this is where we're going to go. On every coin, there are two sides. With all of this miraculous advantage, all of this quantum weirdness turning our lives into the next paradigm, there's also a lot of downside, right? And this, we're going to talk about cryptanalysis. We're going to talk about the threat to public key encryption. So post-quantum cryptography, which is one of my specialty fields, is designed to come up with solutions and new ways to protect data that are quantum resilient. We don't say quantum proof because we don't really know, but we think quantum safe, quantum resilient. More and more, we're getting better and better at this. We don't have all the solutions yet, but we're working feverishly on this. So everything I'm going to tell you, we're working on. We're going to save you, don't worry. And then the harvest now, decrypt later problem. And this came up before. So the fact is that one day, what we call Q Day, there will be a bad actor, presumably a bad actor nation state, that will have the money and resources and talent to actually build a quantum computer with enough qubits that are stable, that are reliable, that will be able to break today's cryptography. It's going to happen. It's not an if, it's a when. And so we're preparing for that day. But until that day comes, we also know for sure that these bad actor nation states are actually capturing encrypted data today, globally, across every industry, across every border, right, across every nationality. They are massively harvesting data that's encrypted that they cannot access yet. And we know that they're saving this data and that they will eventually be able to access it. We're also working on this problem. This is a little bit harder and it's a little bit more urgent, right? So, and we have to really consider sort of the shelf life of data, right? So some data has greater longevity than other data sources, right? So a lot of that work is going on. And it's not just me, thank God. It's not just Wells Fargo. It is a collaborative effort that's happening all around the world, right? And that I'm really, really fortunate to be a part of. All right, so what really is risk? So we're going to get into a little bit of cybersecurity stuff here. Hope it doesn't blow your minds. They're probably blown already, but that's okay. Try and follow me here. So there's a lot of ways to describe cryptography, okay? Cryptographers are inherently really, really smart people, and so when you get two cryptographers in a room, you usually get 4 opinions. So this is one way to describe it, a way that works for what I want to illustrate, right? There's 2 main buckets. There's what we call public key cryptography or asymmetric cryptography, and then there's symmetric cryptography. Now, you may have heard of terms like RSA or TLS or SSL. You may have heard of these things, or HTTPS. Everybody's heard of that, right? And that's all part of this sort of public key cryptography infrastructure. And the way that works really briefly is that if I want to exchange some data, say with Joe, I create a key pair. I create a private key and I create a public key. And I send that public key to Joe. Joe can use that public key to encrypt that data and send it to me, and only I can decrypt it because I'm the only one with the private key. Now, Joe's going to do the same. He's going to send me his public key, and I'm going to use that to encrypt my data. I'm going to send that data to Joe, and Joe's going to decrypt it because only he has the private key. Here's the problem. That public key is constructed in a way that leverages multiplying 2 very large prime numbers together to get an enormous product. And that enormous product is one of the foundations of that public key. If I can factor that enormously large number into the prime constituents, I got access to his data. I can break the public key, I can derive his private key, and now everything that he sends me, a bad guy can decrypt. That's what quantum computers are going to be able to do. They'll be able to compromise every public key in the world and probably do it in real time. So, wow, pause to consider that. So symmetric cryptography. So how this works essentially is somehow I get essentially a random string of ones and zeros, very, very long string of ones and zeros. Somehow I get them over to Joe. There's a lot of ways I can do that. I can mail it to him. I can drive it to him. I can figure out a way to digitally do it with some confidence. But let's say I get that key to Joe. So Joe uses that key, and we'll call it a private key or a symmetric key. I have the identical symmetric key. We have exactly the same keys, right? So he encrypts all his stuff, he sends it to me because I have the same key, I can decrypt it all. Sounds good. And it's pretty secure because those keys get pretty long, right? And instead of having to mathematically guess what the numbers are in the equations to create it, it's just a random string of bits. So to break that key, I essentially have to guess all the possible combinations until I hit that one correct sequence. Oh, wait a minute. computers guess stuff. Quantum computers guess stuff really well. Uh-oh, yeah, that's also in danger. Maybe not as quickly, because it's a lot harder to guess a sequence of thousands and thousands of random bits. It's a little bit harder than factoring a number, not much. It's a little bit harder. So we're a little more confident about symmetric cryptography. But then how do I get the key to Joe? Right? So that cryptography is great, but how do I get it to him? So we're working on all of these problems. But that's essentially how the landscape of what we're looking at falls into these two main buckets. Oh my God, I have 3 minutes. Okay, this says the same thing. Look, I can multiply two numbers together and I can get the product. Anybody can do that on your phone. Go the other way. I challenge you to go the other way, right? That's what we're talking about. That's the problem. Okay, so I'm not going to spend time on this because I really want to take questions. So we are building, oh, this is the last slide. We are building a quantum safe world. I and a lot of really
Peter,
smart
just so
people.
you know, you are the last day, so you don't
I'm
have to
last gig.
you don't have to push it. But
All right.
you know,
Well,
we
bring
can
the
get to
bar in
questions.
here, man. Let's make this a party. Let's do it. Let's drink while we can. So I go around the world and I inform all of the stakeholders, financial firms, communications firms, product developers. I inform them of this. We go into a lot more detail and we build a collaborative relationship. And I think I said this at the top. I and a lot of really smart people around the world are working on this problem. We are developing mechanisms to communicate using quantum entanglement. We're working on cryptographic approaches that use superposition. We're working on devices that could potentially use quantum tunneling. So the idea is, if all of biology and all of reality is based on quantum processes, as we've just talked about, why can't we use that to our advantage to build an ecosystem based on quantum technology that makes you and your data absolutely private and uncompromisable? A world where everything that you send is secure no matter what. And I'm talking like no NSA, no matter what. Like nobody can eavesdrop in. Nobody can figure out what you're sending, right? That's the world that we are working on building. And it's not going to be tomorrow, may not be in 5 years, and it may not be in 10 years. Well, it better be in 10 years. But that's what we're working towards, right? So have some hope, have some light at the end of the tunnel, right? Thank God it's not in my hands, it's in smart people's hands. It's all going to get handled. So yeah, you'll be able to sleep tonight, even if you don't drink. So there we go. Thank you, thank you, thank you, thank you. You guys are awesome. Yeah, we can take some questions. Do we have questions? Okay, here we go. This is like running a roulette wheel. What are we going to get?
Are there any applications for quantum computing on the obfuscation, on the encryption side? Like, can it be used as a tool to make encryption better instead of just breaking it?
Yeah, great question. Are there any applications for quantum computing on the cryptographic side to improve the level of cryptography? The answer is probably yes. I don't know if they're granted yet. There's a lot of work being done in that area. My team and I have at least come up with one or two approaches to doing something like that. There's nothing in the field today, let's put it like that. But yeah, that's definitely something that we would like to be able to do. There's going to come a time, and I say this sometimes out there in front of the rest of the world, there's going to come a time when mathematics will need to be so complicated to prevent a quantum attack that they're just not feasible. There's too much cost computationally, or from a data transit standpoint, too much latency, too much overhead, right? And that day may come sooner rather than later. So we're also keeping an eye on that, where physics may be the only way to secure the world's data transmissions, right? That's what I personally believe. I get slapped around for that, but I know it's coming.
Hey, we got a mic passing around, so.
Yeah, let's do that.
Peter,
Uh-oh, I know you're a smart guy. Uh-oh.
don't say that. My question is a little theoretical, but it's something that haven't been able to ask anybody who's. Anyways.
Okay, just blurt it out.
So, in as far as like quantum mechanics goes and how they kind of broke Newtonian physics in some ways, and we're seeing these things like quantum entanglement being able to surpass the speed of light. I never thought that was really a feasible idea. That the speed of light was the max. That didn't seem like it made any sense. Do you think that if we're talking about string theory and things being broken down and split into all these different dimensions, that really all we're seeing in quantum, the quantum world is that you're seeing kind of another dimension of reality where we're seeing at the smallest scale can interface with our very primitive physical reality that we see, and that there could theoretically, because it's all based on math, be an infinite number of dimensions because of that, and that we're just kind of seeing one instance of it.
Yeah, great question. Sorry, did I cut you off? Is there more to that? No, it's fine. Because that was a lot already. So okay. I'm glad I don't have to repeat the question. I'll come up with the answer. Okay, so mathematically, let's cover a couple of fundamentals first. So mathematically, I'm told, and I've read, and folks have demonstrated to me, that there are 11 dimensions. And it works mathematically when we talk about string theory. If we use the number 11 as the number of dimensions, a lot of equations fit together and they work out nicely, right? And so mathematicians will tell you that there's a high probability that there are 11 dimensions. We're never really going to know for sure, really. But yeah, that's what that is. So what's really cool is at the Planck length, the smallest length of vibrating filaments, we actually now begin to understand the geometry of those vibrating filaments. And we can actually quantify the number of possible permutations of that vibrating filament. And I think there's, going back on memory here, I think there's like 168 possible geometric configurations of that filament at the basis of reality. The one that works for us is one of 168. So why is it that? Why isn't one of the others, right? I don't know. I'm not like I can answer the question. But we know that any variation from the geometry of that filament would produce an entirely different universe. So maybe there's 168 universes, different universe realities, one for each geometry. But maybe some of them don't work because they collapse on themselves. If you tweak any of the parameters of our universe, whether it's at the quantum level or at the classic physics level, if you tweak any of these little parameters, the whole universe doesn't work. The only reason the universe works is because we have this obscure, absolutely impossible combination of physicality and the way that it's constructed. It's almost impossible that this should be the way that it is. I mean, it's mind-blowing. And if you read that book, Biocentrism, Lanza goes into some of those parameters. Some of them are really obscure. Some of them are really fundamental. Some of them are like, if you're off by even 0.0001% in the most obscure thing, the whole universe doesn't work. So that the universe works, maybe it's the only dimension. Maybe the others only work mathematically. I don't know. But boy, I love thinking about it, right? Great question. Okay, do we have any other questions?
Okay, I asked this earlier, and actually I'm going to talk. There's a book that I followed on that same theme of I don't have enough faith to be an atheist. But entangled particles and a vault, and then a paired entangled particle, like say in everybody's phone, a way that potentially could encrypt. But you brought up that these particles are delicate in various ways, and I would love for you to say both the whole entanglement security fact, but also why are they delicate? What makes them not a great multi-release sort of an opportunity to encrypt stuff?
Wow. So first things first. Part of the problem with entanglement is as soon as you measure one of the particles, the entanglement relationship collapses. Okay, so they're in essence no longer entangled. That's part of the problem here. They're like one-time use. Now, in cryptography, that's super useful, right? One-time use passwords, OTPs as we call them, right? That's really cool security mechanism. So leveraging the properties within the boundaries of what it has to offer, we can still use entanglement for things like authentication mechanisms and stuff. you just need to be really, really careful about what we call the coherence time, right? So how long that entanglement lives is subject to a lot of environmental conditions, a lot of other sorts of things, right? And I don't have all of that information. I can't go into a long dissertation on that, but I can tell you that that working through the robustness of entangled particles is a real challenge. So like when you transmit an entangled particle over a fiber optic line, it loses a certain amount of energy the longer it goes. So inherently, the ability to shoot that entangled particle in a contained environment like a glass fiber really tops out about 1,000 kilometers. Any more than that, and there's too much loss over the line, and it just doesn't work, right? And free space is a little bit different. In free space, like if you're shooting to a satellite or you're shooting from drone to drone or things like that, you have not that limitation, but you have other limitations. So you have atmospheric and environmental conditions. Any other particle that interacts with that entangled particle could break the entanglement. There's all kinds of logistical issues with that. But within those confines, yes, it will be one of the fundamental principles of data protection in the future. There's no doubt about it. Hope that answered your question. Doesn't matter if it does, because we're going to move on. Okay.
So someone once brought up to me that, like, you can kind of think of physics also in a security context of like zero-day vulnerabilities,
Yeah.
where you discover a vulnerability was the splitting of the atom. Now we have this very practical zero-day exploit in the atom that you can use for practical purposes. Why hasn't that happened since the splitting of the atom? Like, I can't really point to a physical breakthrough like the splitting of the atom that has had the same impact since that occurred.
Well, you know, that's an interesting question. I don't know that it's a technological question as much as it's maybe a physics or logistical question. So splitting the atom is part of this whole quantum technology conversation, right? So it never would have happened had quantum mechanics not been developed, okay? So things like atomic chain reactions and things like that really enabled that level of technology to progress, all based on quantum theory. Now, I don't know, is splitting the atom bigger impact than absolute positive data protection worldwide for all mankind? I don't know. I think it's a matter of perspective, maybe. Maybe it's a matter of, pardon the expression, relativity. Everything is relative in terms of its impact, right? So, and then how you deploy it, right? So if they'd split the atom and they were able to do a chain reaction, who cares? But that they built a bomb and that they dropped a couple of them on Hiroshima and Nagasaki, is that the impact you're talking about? Or is it the ability to come up with a controlled fission reactor to create electricity in a different way? Is that the big impact that you're talking about, right? So I don't know. I mean, I'm not trying to dodge the question, but I'm trying not to answer it too. So does that make any sense? Yeah. Okay. All right, moving right along. Or do you have a follow-up?
Kind of wondering, like, is there another, like, one of the other things that I've heard brought up too is like string theory hasn't had any impact yet. Like some people have started, not impact, some people have started their career in string theory and now today, and there hasn't been like, you know, a serious physics breakthrough, I guess, due to the theory. Is there alternatives, or is that just, you know, we're just in a lull?
Yeah, there are. There's a number of permutations, there are a number of different tangents that people are going on. There's supersymmetry theory, there's superstring theory, there's lots of flavors, right? There's no one path, and they all think they have the right path, they all think they're going to have the right answer. But I want to challenge you about the impact of string theory, of nothingness, of uncertainty. So, and I wasn't going to do this, but I'm going to do this. So, that the world exists because we observe it. That particles know you're going to observe them before you do gives you the ability, at least in theory and for some people in practice, that now you have control of reality. So let's say for a minute that nothing's real until you observe it, perceive it, define it. Theoretically, then, you could think, perceive, manifest unlimited. If the world exists because you observe it, then how you observe it flavors the world. There is an inexorable link between us and reality. And maybe string theory, maybe quantum theory gives you control over reality that we are completely oblivious to. Maybe the evolution of man and the point of string theory to discover that this is the way that it works is in fact the mechanism that brings us to the next evolutionary level of being able to literally manifest permutations of reality, whether it be over a month, a week, a second. Maybe this is the mechanism that is the next evolution of life. Maybe understanding this is the key to everything. But that's next year's topic.
It's more of a comment on the whole of quantum physics. We're definitely in a simulation. That's crazy.
I like that. Yeah, there's been a lot of work, a lot of theory on that simulation thing, right? I think we'll probably poke holes in it after a couple of martinis, but yeah, no, certainly a possibility. There's no doubt about it. Any other questions?
This has to be the end of cryptocurrency, doesn't it? I mean,
I hope so.
the giant
No.
long.
I wish.
That's
Oh my God. Oh, that's what we need is another fiat currency. No, we can protect cryptocurrency just like we can protect any data payload. So it's based on blockchain. Well, most of them are based on blockchain, this construct, right? Blockchain is sort of the utility knife of distributed ledgers, right? We can provide controls and we can provide all kinds of measures to protect cryptocurrency. There's a place for that in the world. Let's be clear about that. I whine about it because my wife wants me to buy a lot of it and I don't want to, and so, you know. Yeah, no, without any economic factors, cryptocurrency, NFTs, all of these constructs will be part of what we're protecting. These are just use cases where the work that we do will apply to, so don't worry, it'll be fine. Just don't lose your wallet or you're screwed. We weren't going to do a crypto thing. Okay, any other questions? Do you have one in the front?
So on quantum, doing a proof, because I was thinking about quantum time, which would be even smaller than, yeah. But if you could prove that basic things are quantum, could you not do a proof that all things are quantum and that there isn't actually any single flowing thing?
Yeah.
And then use that as encrypting?
Yeah, maybe. I don't want to, okay, so I don't want to answer your question. Okay, I want to go down a slightly different road. And I don't know if for those who are really reading the slides, you might have caught this, okay? Time is an illusion. There is no time. There's no such thing as time, okay? It can't be quantified. It actually can't even be measured because it doesn't exist. We create this construct of time out of our evolutionary past. The ability to predict one's next move based on what happened yesterday, that illusion of cause and effect, that's what propagates and protects species to survive. So where a species can thrive, it can use that sort of yesterday, today, tomorrow paradigm to help it thrive in the world. But at the quantum level, and we can demonstrate this all day long, at the quantum level, there is no time. There is absolutely no distinction between cause and effect. Now, we don't have enough time to go into all the details here, but we can demonstrate that a particle doesn't have any sense of time. There's no distinction between what happened yesterday and what happens tomorrow. It's all the same thing. But we have to have it. We have to have it. We absolutely must have it, right? It explains everything that we see. It explains the orbital paths of planets. It explains the Big Bang. It explains why our kids grow up. It explains everything. And every life form on the Earth has that same context. Doesn't make it real. It makes it perception. And again, Lanza's book, goes through this as well, right? He has a very good explanation for how time is a necessary, absolutely necessary illusion. So to answer your question, I think we're getting closer and closer to demonstrating and proving that there's no such thing as quantum time. People have been working on it and trying to calculate it and all of this stuff, and it's been futile. There's never been a successful effort to come up with the equations to explain the smallest unit of measurable time, right, in a completely objective way, right? We use time to measure, we measure time by the change from this state to that state. That's how we do it. There's something other now than there was not now. Or there will be something next that isn't now. That's what we call time. But in the quantum world, it doesn't work that way. There's no cause and effect. Things have an effect before the cause happens. And we can prove that in the lab over and over. So, whole nother presentation going on there. So anyway, sorry
All right.
if I got too off the rails.
Unfortunately, there is no illusion for Treefort
Yes.
happening next. So thank you very much, Peter.
Thank you all.